All right, welcome everyone. I'm sitting here in my office hours. Had a few people join earlier on, but right now there's no one, and so I thought it'd be a good time to maybe do a problem here from WebWork. I know from Piazza and whatnot, it seems like you guys want some more help with homework 30. So this is about Green's theorem and Flux and all that sort of stuff. And so I thought, yeah, this would be a good time to do a problem and kind of talk through my steps and how I would tackle a problem like this. So my WebWork problem has this vector field here and these particular curves. And I think these are the same for everyone. And then it asks to calculate out the outward flux. So the outward flux over the entire region, because this is a closed curve, right? When you look at this entire thing together, right? Not only have this parabola, but also the straight line. This is going to be an application that we can use this other form of Green's theorem, the flux form of Green's theorem. But this actually asks to calculate out each one of the line integrals for each particular piece as well, because you can calculate flux with just a curve. And so it would like us to do kind of all of that. And so what I'm going to focus on here in this video anyway is calculating the flux on this particular piece, the y equals x squared, as x travels from 0 to 1 here on this particular vector field. So that's my goal here for this video. First of all, just kind of to back up, even before we get into the calculations, I just want to remind you, right, flux is talking about how much stuff is leaving or entering in a particular region. So in this case, we have a two-dimensional region, x's and y's, right? And I kind of think about if I was to draw, maybe I was on the beach or something, I would draw, maybe lines on the beach, with a twig or something like this. And I want to know, like, maybe this is pretty close to the water. And I want to know, is there more water entering into this region or exiting the region for a particular instant of time, right? And so outward flux would say, right, let me just write this down for outward flux, like we have here. If this ends up being positive, so here's my flux integral right here. If this is positive, right, and when I choose this to be an outward normal vector, then more is leaving or going outward than coming in. On the other hand, right, if I had done something different, right, and I wanted to calculate out inward flux, let's suppose you calculate out inward flux. So this normal vector here is now chosen differently so that it's an inward pointing normal vector. Then in that case, if this was positive, then we would say more is coming in. Than what's leaving. And so that's kind of what this normal vector is acting as. You have to decide, are you counting positively the things that are coming in which case do inward flux, or are you counting as positives the things that are going out, right? And so in that case, that would be outward flux. So that's what flux is. When we actually do the calculation, especially when it comes down to, right, we're not using Green's theorem yet, we're just going to be doing on a particular piece of a curve, it's a lot like what we did in 16.2. So let me just kind of write down my integral again here. So we're doing flux, in this case, outward flux, f dot n ds. And the only change is, right, when we were doing in 16.2 line integrals with vector fields, we were calculating out work, in which case this n here, it was replaced with a tangent vector, right? So in that case, you're calculating out work. Here, we're calculating flux. Still, though, the methods are going to be very similar in that we want to transform all of these pieces into things with t's. We have a single integral here. We want to get everything in terms of t's. F in terms of t, n in terms of t, everything in terms of t. That's going to be our goal. And so the first thing that we want to do is figure out, what does our curve look like in terms of t's? So remember, I said I'm going to do just this one piece here for this video, the y equals x squared. So if I wanted to parametrize this, y equals x squared, and again, I'm going back and I'm thinking about 13.1 and harnessing all my knowledge about when we parametrized curves for the very first time in this class. And in this case, I think setting our variable x to t makes a lot of sense. And then in that case, if y is equal to x squared, then the y component is just going to be equal to t squared, right? Because x is t in this case. So this is going to be t squared. And then because x ranges from 0 to 1, that means we want t to range from 0 to 1. Okay, with this here, we can already put our vector field in terms of t's. So I could go ahead and start replacing in, everywhere I see, instead of x's and y's, I now have an x component and a y component that has t's in them. So let's go back to my vector field here really quick. The x component, or the first component here was xy. So this is going to be xy. And then the second component was y squared. So y squared. So that's one thing that I've transformed all in terms of t's. Now, next up, the normal vector. The normal vector takes a couple of steps in order to get this out. The first thing that you want to do is find the tangent vector. So first we're going to find the tangent vector. The tangent vector for the curve is going to be r prime of t. Remember, this was back from 13.2 when we first learned about what does this thing actually mean. It's the tangent vector. So we have the tangent vector. This be 1 and 2t. And remember, that's just we take the derivative of each piece. Now, if you want a normal vector for this, you're going to swap the components. So I'm going to do n, so normal vector here. We're going to swap the components, and we're going to make one of them negative. So we can either make the y component negative, or we can make the x component negative. And remember, the normal vector here is what's going to be determining, are we calculating out the inward flux or the outward flux? We want to make sure that our normal vector is pointing outwards. So if we want our normal vector to be pointing outwards, notice that all of these pieces here, right, all of these purple arrows are pointing a bit downward, right? So here they're pointing more downward, downward, downward. Here they're pointing a little bit less downward and more off to the right, but all of them are pointing a bit downward. So outward and downward in this particular case are synonymous, right? They mean really the same thing for this curve. But again, you really have to draw the picture. You have to look at this in order to figure this out. So if we swap these, and remember, I want downward, then that means that I would like to take my second component here, my y component, and I'd like to apply the negative to this piece. So this is the rule. I'd like to talk to you a little bit about why the rule works, right? And so with that, I'm just going to draw a little fake curve over here. And at a particular point, suppose we're going this direction here, you have the tangent vector. So remember, the tangent vector is this here. If you want instead a normal vector, right, a normal vector, something like this, notice that the tangent vector and the normal vector are always going to be perpendicular to one another. And so really what you're trying to do is that you're trying to find a perpendicular vector, right? And so this is saying, in order to do this, in order to come up with a perpendicular vector, swap the components and make one of them negative. And let's see what happens, right? So if I take these things and I dot them together, remember the dot product was how we checked for perpendicular. If this works out, then hopefully the dot product should be equal to 0. And so by swapping them, notice you're going to have this mismatch here. You're going to have the 1 times the 2t. So you're going to get 2t here. And then we add together. And when you multiply the other ones, 2t and -1, you get the negative 2t. So by swapping them and making them negative, you kind of make sure that each one of these pieces has a has each one of these, but one's positive and one's negative. So they're always going to perfectly cancel out and always give 0. So that's why that strategy works. But notice if I had made the other one negative, right, that would still work out. It would still be perpendicular and everything, except for then maybe I'd be finding, this normal vector. So that's where you're choosing. You do want to count the things that are going in this direction, or do you want to count the things that are going in this direction? So that's where you have to read in the problem and say, you know, does it want upward flux, downward flux, inward flux, outward flux? What is it looking for? And then you look at your picture and you try to figure out, okay, where should I apply that negative to make sure that I'm counting things in the correct direction? Okay, so I'm fairly happy with this. All right, sorry, I had to hit pause. A student actually came to office hours. And so I've lost my spot a little bit. I think I kind of know where I'm at. But I apologize if there's a little bit of gap in some explanation. Yeah, so we have here the normal vector now. The issue and why I decided to use little n here rather than capital N is remember that this capital N here is supposed to be a unit normal vector. And so if we want a unit normal vector, well, we need to divide by the magnitude of this thing. And so let's go back here. I see that I've taken up my space that I was going to use for this. So I'm going to go ahead and shrink this down, cheating using the magic of technology here. And so we again have calculated out the normal vector. I have 2t comma -1. And in order to make it a unit normal vector, we're going to divide by the magnitude. And so the magnitude here, we divide by the square root and we square each piece. So 4t squared plus 1. Something remarkable actually happens here when we take and we transform the ds, right? So I'm also going to turn the ds into dt. And so remember, if we wanted to do this back in our 16 2 days, ds, and now I need to find a spot to write. I have all my primo spots that I want to write, you know, where all of this stuff is are already taken. So I'm going to move this down a little bit. So ds back in our 16 2 days was equal to the magnitude of r prime of t dt. This was the transformation that we needed to use. And remember, ds right here is just like a small step, right? S being like the parameter, the variable that's typically used for arc length. That you can think of this as small step or a small distance. This right here, the magnitude of the derivative, right? This was speed, right? It's a lot like velocity. So velocity or the tangent vector is r prime of t, and then with the magnitude there, that's going to be speed, and dt is a small time. So that's at least one way to think of it. So then if you look at it in terms of the, you know, physically what's going on here, really this is just distance equals rate times time. And so this really isn't a bad formula to memorize just because we already know probably distance equals rate times time. Okay, so with that ds, I'm going to go ahead and put in the magnitude of r prime dt. So r prime, again, we've already calculated out. And notice, because these have the same components, just reordered as our normal vector here, when you go ahead and you take the magnitude of this, you get the square root of 1 plus 4t squared. This ends up being the exact same thing here, always. And that's the nice bit, is that because your normal vector and your tangent vector have all the same components, but they're just rearranged and one's made negative. Well, when you take those things, you square them, you add them together, you throw them under a square root, they're always going to be the same quantity. And so these are going to nicely cancel out. And so as you do more and more of these problems, you'll get to a point where you say, I don't really even have to write this down anymore because I understand that it's always going to cancel. All right. Finally, let's go ahead and evaluate out our dot product here. Now that we have everything in terms of t's, we should put our boundaries in terms of t's. Remember, t is ranging from 0 to 1, and that's just from my parametrization. So that's based on the curve here. T is ranging from 0 to 1. When I evaluate out my dot product, so I have to do here, do in green. Let's see, that's t cubed times 2t, so that's going to be 2t to the fourth. And then here I have t to the fourth and times -1. So that's going to be negative t to the fourth dt. And so, of course, we get a little bit of cancellation. And we just are integrating from 0 to 1, t to the fourth. And when we integrate this, we get 1/5 t to the 5th, plug in 0, plug in 1, and we just get out the final answer of 1/5. So that's the result for this particular piece. Now, of course, when you do the other piece, right, there's two pieces here. There's the parabola, which we just did, and then there's the line. Of course, you're going to need to essentially do a different problem. You're going to reparametrize this. You need to calculate out your tangent vector again. You're going to need to calculate out a different normal vector, all that sort of stuff. And so you have to treat it almost like a separate problem. All right. I hope that this has been useful, guys. Take care, and please reach out on Piazza or via email or wherever if you have questions. See you.